Только сдвинуто.
Я toujours le problème de
Я так понял, Игорь, да, ты с них все развиваются, да.
Bon, j'ai changé les nuances, c'est parce que... Ok, peut-être, par exemple, ça ok. Et je te dirais vraiment quand est-ce qu'on ok. Moi je te dis, je sais. Non, ça c'est pas vrai. Il faut tout le monde mette des alors on passe. Ok, il fallait que tu restes ah oui, c'est ça. Non, parce que c'est pas ça. Oui, ça c'est pas que je revienne, parce que je revienne les choses. Eh oui. Ok. Bon. What do we have with you? The last price I could remember was
near 10 now. It's about 10.
Is that what we pay internally with a certain amount?
No, we get a rebate on that for gas.
So technically, it's what you would pay with a regular customer. So it's about £10. So maybe €12 or something like that. Yes, I know.
Dear colleagues, ladies and gentlemen, it's time to open our afternoon session. This is the physical session. This main results devoted to parahydrogen induced polarization. And as I see, the session which was reported people from the Siberia, east and cold part of Russia, but with very deep tradition in understanding of physical phenomena and application. And I'm glad to introduce the first speaker, Igor Kopchuk, who is head of the laboratory of tomography in the Siberian branch of Academy of Science, and talk title. Please, Igor, I would like to ask you, you talk within 25 minutes. Sorry, 25 minutes, not to save time for questions.
Yep. Okay. Thank you, Mr. Chairman. Welcome back to the next session. We'll switch modalities here. We've heard about optical pumping of gases like xenon and helium-3. We heard this morning about dynamic nuclear polarization, and in particular about dissolution DNP technique. We'll switch now to parahydrogen and parahydrogen-induced hyperpolarization. And of course, dissolution DNP is probably the most advanced and the most sophisticated technique. So if you compare people who do DNP with computer science, for instance, it'll be probably cool guys working with fancy instruments. And compared to that, the FIP community would probably look something like this. And of course, DNP is very powerful and very advanced, I would say, at this stage, even though there are still many problems. There are advantages with the FIP, and the main advantages are that it is much more simple, it is much less expensive, and also, in fact, much faster in producing hyperpolarization. So let's start with some introductory slides. This has been already explained, I think, that under thermal equilibrium, the number of spins up and down is pretty much equal except for at about 600 megahertz, for instance, we have 10,001 spin pointing in one direction and 10,000 spins in the other direction, meaning that these 20,000 basically cancel each other. Only one spin out of 20,000 gives you an observable NMR signal. So in hyperpolarization, we're trying to create the situation where all the spins, or most of spins, point in the same direction, and this can provide signal enhancement of an order of 10 to the 4, 10 to the 5, or even larger. So we use parahydrogen to achieve this, and I will remind you that there are two spin isomers of molecular hydrogen. One is called orthohydrogen. This is the modification which has the total nuclear spin of 1. And there is parahydrogen with total spin, nuclear spin 0. Normal hydrogen is a 3-to-1 mixture. This is room temperature, normal statistical, basically, ratio of ortho and parahydrogen. But it is pretty simple and straightforward to produce samples enriched in parahydrogen. In fact, almost pure parahydrogen can be obtained. Parahydrogen has no nuclear spin 0, so it gives no NMR signal. But the important thing is that its nuclear spins are correlated, and this is what is quite useful for us. There is another way to look at this. You can, when looking at parahydrogen molecule, you can say that basically these two hydrogen atoms spend a lot of time together in the same molecule, so they get to know each other quite well. And when you do a chemical reaction, then it hydrogenating an unsaturated molecule or unsaturated chemical bond in the molecule with parahydrogen. What you need is for these two hydrogen atoms from the same molecule to end up in the same product molecule. And this is what we call pairwise hydrogen addition. And in this case, we can expect signal enhancement or hyperpolarization. If the addition of hydrogen is non-pairwise, then these two hydrogens do not know each other. They come from different H2 molecules, and there will be no hyperpolarization. So the important thing to have is this pairwise hydrogen addition, meaning that both hydrogen atoms from the same H2 molecule end up in the same product molecule. So there is a known way to do this, and this can be done by homogeneous catalysis in solution. So basically you have your catalyst, for instance, the sodium complex, which is known as Wilkinson's catalyst, dissolved in an appropriate solvent, and also your substrate, which you would like to hydrogenate here. So you introduce parahydrogen into the solution, and then through this catalytic cycle, these two hydrogen atoms stay together and end up with the same product molecule. And this is where we can expect hyperpolarization. And this has been realized, as you can see, in 1986 by Bowers and Weidekamp. This was predicted first theoretically, and then a year later they have demonstrated this effect experimentally in hydrogenation of this compound into this one. The phenomenon was abbreviated to Pasadena, and I think the reason is quite obvious why this was called Pasadena. There are two basic modifications of this FIP experiment. One is called Pasadena, and this is when the reaction with parahydrogen is done inside the high magnetic field of the NMR magnet, for instance, when the sample, the catalyst, and the reactants and the products stay inside the magnetic field, high magnetic field all the time. Another modification is called Altadena, and this is when the reaction is done outside the NMR magnet in a low Earth magnetic field, and then polarized products are transferred into the NMR tube or MRI scanner for observation. This is called Altadena. Now, so when we hydrogenate, for instance, an alkene with a double carbon-carbon bond with hydrogen, we produce this alkane molecule, and this is what normal NMR spectrum would probably look like, with two NMR lines, one for the CH2 and another for the CH3 group. If we repeat this experiment with parahydrogen, and if we have pairwise hydrogen addition, well, first of all, we have non-pairwise hydrogen addition, then nothing happens. If the addition of parahydrogen is non-pairwise, we'll get exactly the same spectrum, no hyperpolarization. But if hydrogen addition is pairwise, then these NMR signals will have a different shape, first of all, different appearance, and it is quite easy to distinguish them from normal NMR signals in the spectrum, but also they are quite substantially enhanced. And enhancement can be quite high, in fact, as we know. So this has been, as I've told you, predicted and demonstrated in catalytic reaction, and then later it has been, in fact, used in vivo. So this carbon-carbon triple bond in this compound, C13 labeled, was this bond was hydrogenated using this cationic radium complex. This was done in acetone solution. So then in this reaction product, the hydrogen atoms are polarized, but then by manipulating the magnetic field, it is possible to transfer polarization from hydrogen atoms to the C13 labeled site here. And then this hyperpolarized solution was injected into the bloodstream of a live animal, and the C13 angiographic image was acquired in less than a second, which is quite impressive, of course, considering that this is done using C13 MRI. Now the technology has been improved, better images have been obtained, but one of the problems with this approach is that, as you may remember, the catalyst, this metal complex, it stays in the solution, so it is basically injected into the bloodstream, which is not very healthy, of course, and this cannot be done with humans, obviously. And also, I should remind you that this experiment was done using acetone solution, which is also not a very nice thing to do. So there are problems. They have to be solved in order to translate this approach to medical applications, obviously. Here's one example how this can be done. In this case, we stick with homogeneous catalysis. But what we do now, we have the solution of the catalyst here, and then we bubble our gas, and also we bubble our substrate, the reactant, which is, in this case, is propylene. So we bubble these two gases through the catalyst solution, and then here at the outlet, we collect the hyperpolarized product, the propane gas. So this spectrum here is obtained for thermal equilibrium situation. You can see the signals here, which are thermally polarized. When we use parahydrogen and flow the gas, this is the spectrum that we get. So you can clearly see the signal enhancement for the propane, for the gas produced. Now I should point out two important things. First of all, this gas is catalyst free because the catalyst stays in the solution and the gas is absolutely catalyst free in this case. Another important thing is that we can do this continuously, unlike in dissolution DNP, where you need some time to produce the sample and then dissolve it. Here we can collect this hyperpolarized gas continuously, or we can just flow it to the NMR and continuously detect the NMR spectra or images. Okay, but this is probably not the universal solution. So the next idea was to switch from homogeneous to heterogeneous catalysis. And the reasons are, first, heterogeneous catalyst is a solid. So if you can use that, then you can probably easily filter it out later when you produce your hyperpolarized products. Another advantage is also that with heterogeneous catalysts, you can do this hyperpolarization protection continuously, non-stop, basically. And also, there is one important issue that in major industrial applications, they usually use almost exclusively heterogeneous catalysis. Only very few processes done on the industrial scale which use homogeneous catalysis. So the first two are important for potential biomedical and probably other applications. And the third one is interesting because this could be used to study the mechanisms of important heterogeneous catalytic reactions. Now, but there is a major problem with this because, as I've shown you with homogeneous catalysis, these two hydrogen atoms, they stay together throughout the catalytic cycle and end up in the same product molecule. This is what we need, the pairwise hydrogen addition. In heterogeneous catalysis, the situation is somewhat different, especially when we use the most common, the supported metal catalyst. For instance, palladium nanoparticles supported on alumina support. And in that case, what happens is that hydrogen chemisorbs dissociatively. So these hydrogen atoms, which come from the same H2 molecule, they separate and then they start to diffuse very rapidly on the surface and eventually lose each other. So there should be no pairwise hydrogen addition. But in order to overcome this problem, we decided to do something slightly different. The idea was to take a homogeneous catalyst and then to link it to a solid support. So this way, we hope they would preserve the reaction mechanism. We would preserve the pairwise hydrogen addition in the hydrogenation reaction, but we would still produce a solid catalyst, a heterogeneous catalyst. So we would have probably both, hopefully, the heterogeneous catalyst, but the homogeneous reaction mechanism. And indeed, this worked. In 2007, we have demonstrated that this approach indeed works. And this has been demonstrated with several catalysts. This iridium viscous complex immobilized on metal oxide. This is hydrogenation of propyne into propylene and propane. And these are the NMR signals of propylene here. As you can see, they have this characteristic shape indicating a substantial hyperpolarization. In fact, if you do this experiment with normal hydrogen, you will see no NMR signals for propylene, meaning that the signal enhancement is quite high. There are a few other examples. I'll probably skip them. The immobilized cationic gold complex also produces some nice polarization. One of the most recent results, the idea is similar but somewhat different, because in this case we're trying not to attach a homogeneous catalyst to a solid solution, but basically to design catalytic center on the surface, like with vanadium oxo species attached to silica, and we have demonstrated that this also works. Hydrogenation of propylene with parahydrogen to propane. You can see these LTD signals for propane here. So this approach works, but again, it's probably not the ultimate solution, not the best one. And again, as I told you, if we try to switch to more conventional heterogeneous catalysts, metal nanoparticles, we run into the problem that hydrogen chemistry dissociatively on the metal surface. That means that these two hydrogens diffuse apart. Then when the substrate molecule comes in, it picks up just random hydrogen atoms instead of doing the pairwise addition. So we should not expect any hyperpolarization impact in this case. But surprisingly, if we use such catalysts, we do observe polarization. Again, this is hydrogenation of propylene to propane using rhodium nanoparticles supported on titanium. And as you can see, for propane, we do produce quite substantial polarization. Now, and we can also do some imaging. So this is just an NMR tube with hyperpolarized propane inflowing through this capillary here into the NMR tube. And then this is the image of our sample. Okay, so there are other examples. I'll skip them. Different metals, different metal particle sizes. You can see that the magnitude of hyperpolarization changes. So we have a lot to play with to optimize this. Another example is like copper nanoparticles supported on for support on silica gel, I guess. Again, some playing with ligands and changing the hyperpolarization levels and things like that. This is an interesting example. The cobalt nanoparticles supported on alumina. Again, hydrogenation of propylene to propane. Now, as you can see, there is a substantial hyperpolarization for propane, which is quite surprising because cobalt nanoparticles are magnetic. They are probably ferromagnetic at the temperatures that we are using. And yet, even we would expect some relaxation of hyperpolarization. We do see some pronounced effects in this case. Now, there are other materials which can be used, not metal particles, but also metal oxides. There was this paper in 2001 by Carson, Bowers, and Weidekamp, who have claimed that they can observe this heterolytic activation of hydrogen on zinc oxide using parahydrogen. So this is the spectrum they detect with normal hydrogen on zinc oxide, parahydrogen. This is the difference. And this claim is the effect similar to Pasadena in solution. Now, as far as I know, no one was able to reproduce this effect. But nevertheless, we have used some metal oxides. For instance, this surprising example is this calcium oxide or lime. Turns out it's a fairly good hydrogenation catalyst. So it can be used to also hyperpolarize some molecules in hydrogenation reactions, some other oxides. Let's keep that. One more example, and this is more sophisticated design of these catalytic particles. This is palladium-indium nanoparticles supported in alumina, and the idea is to dilute palladium with indium atoms, hoping that the diffusivity of hydrogen atoms on the metal surface would be much, much lower as compared to palladium surface, for instance. And in fact, indeed, this catalyst does produce substantial hyperpolarizations in hydrogenation of propane into propylene in this case. And it's a fairly selective catalyst. Okay, so and then we can actually, for this example of the hydrogenating propane into propylene, we can produce images using different NMR signals of propylene. So if we do it for thermally polarized gas, we basically see nothing. But if we hyperpolarize propane by hydrogenating propane into propylene, then we can do the same. In this case, of course, because of the hyperpolarization, we do get some meaningful images. Well, this maybe. We have also demonstrated another important thing, that in fact, for biomedical applications, you would need to produce your hyperpolarized molecules in an aqueous solution, obviously. And this is a demonstration that we can produce a number of hyperpolarized molecules in aqueous solution, in this case using a homogeneous catalyst by spraying this mixture into a certain volume and then detecting the hyperpolarized NMR spectra. But more importantly, we can do the same using heterogeneous catalysis. And this example shows you the production of this compound with N15 hyperpolarization. So basically, we hydrogenate the unsaturated precursor, produce hyperpolarized hydrogen atoms, and then we transfer polarization from hydrogens to N15 nuclei by doing this reaction in the magnetic shield, in a very low magnetic field, basically. As you can see, we can produce quite substantial and fairly long-lived hyperpolarization for N15 nuclei. You can see that at the lifetime of a few minutes, this is N15 hyperpolarization. We have also made some steps toward biomedical applications. And in this case, for instance, what we do, we hydrogenate vinyl acetate, and we do it in the gas phase. So first of all, we bubble parahydrogen through vinyl acetate liquid, which evaporates, and then its vapor together with parahydrogen goes here to this catalyst, and this is where the reaction takes place. And then the gas keeps flowing and gets dissolved in this solution, which contains base. So after the hydrogenation, the hydrolysis takes place, and as you can see, we produce here an ethanol and acetate, and ethanol demonstrates you hyperpolarization, this Pasadena signal. And the important thing again is that the solution is completely catalyst-free, because the catalyst stays here and the reactants flow through it, and it's a continuous wave sort of production, and also producing catalyst-free hyperpolarized molecule. And a different experiment was done, a similar experiment, but done slightly differently. It is the same reaction, but the molecule is labeled with C13 here, and then by transferring polarization from hydrogen atoms to C13, we produce C13 polarized acetate here. And again, this is heterogeneous catalysis, so it's pretty easy to remove the catalyst. Well, the very recent paper where it is demonstrated that we can probably even produce hyperpolarized pyruvate and acetate using parahydrogen by synthesizing the appropriate precursors. This approach is known as sidearm hydrogenation. So there's a sidearm which is introduced in the molecule chemically, and then it is hydrogenated, and then later the molecule is hydrolyzed, and this is in fact possible to produce pyruvate, acetate, other molecules in a hyperpolarized state using parahydrogen. There's also, I mentioned that this approach is quite interesting for catalysis, and in fact we can use the signal enhancement to try and study catalytic reaction mechanisms. This is not the subject of this this meeting, but I'd like to mention this anyway, and in particular here's an example where we can study how catalytic microreactor operates. So we have a catalyst bed here, we flow the substrate and parahydrogen through this catalyst bed, and we can observe using MRI how the polarized product is produced along this microreactor. I should also mention another possibility. I've been talking about hydrogenation reaction using parahydrogen, but there's a different approach called SABRE, where there is no formal hydrogenation. The molecules are brought together temporarily on the metal complex, pyridine in this case, and parahydrogen. There's polarization transfer from parahydrogen atoms to pyridine, and then pyridine dissociates, goes back into the solution, and this is another approach which uses no formal hydrogenation, so basically requires no unsaturated precursors. We've published several examples of this approach, and also some recent one, and this includes some proton and 15 imaging. But there'll be another talk on SABRE, where more examples will be provided. So I'll just skip this one, except I'll mention that with SABRE, they usually, again, use homogeneous catalysts, but there are now techniques either by filtering out SABRE catalyst, or in fact, by using immobilized catalysts on silica, for instance, which can be used to do heterogeneous SABRE. So in this way, it is possible to hyperpolarize and then remove the catalyst rapidly. Okay, so two more points which I'd like to mention. Now we're talking about removing the metal because it is toxic, but in fact it turns out that it is possible to use metal-free catalysts to produce hyperpolarization, to do hydrogenation. And one example is using these systems called frustrated Lewis pairs, which contain no metal atom, and yet they can activate molecular hydrogen and then produce quite pronounced hyperpolarization for this NH and pH ways here, and also N15 polarization has been produced. Another thing, another possibility, we use parahydrogen, but in fact, it is possible to do similar experiment without using any hydrogen. And the reason is that in addition to hydrogen, there are other symmetric molecules which can be used in a similar way if we can produce them in certain spin state. The problem is that while it's fairly simple to produce parahydrogen, it is almost impossible to produce other symmetric molecules in certain enriched spin states. And let me just conclude with this example. What we're trying to do, we are trying to produce this so-called spin isomers of ethylene, the analogs of this parahydrogen or hydrogen thing, chemically. So we start with acetylene, we hydrogenate acetylene with parahydrogen, and we produce ethylene, and hoping that the correlation of nuclear spin states of parahydrogen will be preserved in the ethylene molecule. In fact, it was possible to demonstrate that we have done this reaction in ethylene, which is produced. The signal is just normal NMR signal, there's no hyperpolarization. But if we use this ethylene in the secondary reaction using this chemical here, we produce this adduct, and excuse me, and this way we can demonstrate that these spin isomers of other symmetric molecules, not only parahydrogen or hydrogen, but spin isomers of other molecules can be used similarly for producing hyperpolarization. And this spin state, these spin isomers can be quite long-lived. So we have demonstrated that spin isomers of ethylene can live for about 1,000 seconds, whereas T1 of ethylene under normal conditions is well beyond below 1 second. Anyway, so just to mention that these spin isomers are in fact important not only in chemistry and biology, but also in astrophysics and astrochemistry, where they derive very interesting information about molecular clouds, protostars, and comets, and sometimes can make very interesting conclusions, like this one, for instance, by measuring the orthopara ratio of the molecules in space, basically. So anyways, this is, I guess, the main message is that, well, there is hyperpolarization paradise somewhere where the signals, NMR signals, goes through the roof. But there are different ways to get there, and one is DNP, which is very high financial energy barrier, basically, but the FIP may be a much simpler and cheaper solution to get to the same place. So this I'd like to thank the group members who have done this work, also collaborators in Noisy Periscope Institute of Catalysis, and also a number of international collaborations. And thank you for your attention.
Questions?
Can you tell how stable these hydrogenated molecules are? So can they be somehow affected with magnetic fields, or how do you have to preserve them for a longer time?
Well, okay, so the molecules themselves are absolutely stable. They're chemically stable, like propane live for years and years, but you're probably talking about hyperpolarization.
Yeah, yeah.
And in those terms, the gases are not, the protonated gases are not very good because the T1 of propane is below 1 second. And yet we think that, in fact, it can be used in biomedical applications for lung imaging. In fact, we believe that we can go to very high polarizations. And there are tricks to preserve the polarization. If we go into to low magnetic fields, for instance, and if we use deuterated propylene hydrogenate to propane, the T1 goes to a few seconds, 5 or 6 seconds or so. If we dissolve it in liquid, then it goes to about 30 seconds or something like that. So there are ways to prolong that. Also, the interesting thing is that there are spin states which live much longer than T1, and this is well known. And in fact, hydrogenation with parahydrogen produces those long-lived states. So there is hope that this can be, in fact, extended. In solution, I've shown you, especially with N15, the T1 can be minutes. So this is much nicer, of course.
Okay, any other questions? Okay.
Yeah, recently I heard talk by Stefan Weber. They're using nanoparticles, but they functionalize them or put chains on there, and the claim was, maybe you can comment, that improves the polarization because it makes the pairwise addition more likely for the.
Yeah, I know this work. Yeah, I know this work, and this is in fact the explanation is very speculative, because this is how we explained our very first results in our very first paper, that we were producing some boundaries basically on the surface to slow down the diffusion. This is just speculative in terms of explanation. The other problem with those studies is that in most cases, when you introduce a ligand, especially if it's a ligand containing an SH group, you are poisoning your catalyst. So the signal enhancement can be very, very large, but the problem is that the conversion that you get is extremely low. And okay, of course, you show you very high conversions, but then you forget to tell people that the conversion is basically zero. And what you need is the product of conversion times signal enhancement. Yeah. So this is nice work, but it is not the answer to the problem.
Short question.
How high is the magnetic field for the reaction?
Now we can do the reaction in the normal NMR magnetic field, or we can do it in the Earth magnetic field, or we can go even below the Earth magnetic field, depending on what we are trying to achieve. The magnetic field does not affect the reaction itself. It affects the polarization which is produced.
about the structure of the catalyst, is it simple crystal metal?
Now, usually they are metal nanoparticles, say 1 nanometer, 2 nanometers, 5 nanometers in that range, supported on alumina or silica or titania. I think probably the best catalyst that we have is those that are supported on titania.
Okay, thank you, Igor, for nice talk. We have to move to the next talk. The next talk should be delivered by Ivan Skovkin of the same institution. The talk is entitled Parahydrogen Drive Hyperpolarization from Homogeneous to Immobilized Metal Complexes.
Hi everybody, I will talk about parahydrogen derive hyperpolarization from homogeneous to localized metal complexes. Today, the application of nuclear magnetic resonance are widely applied in science, medicine, and industry. However, the low sensitivity is still main drawback of this application. What is means for this? This is due to the fact that energy interaction of nuclear spins with magnetic field is low. This leads to the fact that different population which determines intensity of NMR signal is also small. In one hand, the increases of magnetic field increase different population, but this approach has low effects because even modern NMR devices, the different population does not exceed hundreds of a person. For this reason, the application of hyperpolarized systems is very promising in solving of problem low sensitivity of NMR technique. Indeed, the spin systems which has a different population about 100% in NMR in 7 Tesla magnetic field, one Oxide enhancement of NMR signal by 4 orders of magnitude. Today, there's several basic methods which can apply for generation hyperpolarized substrate, which is optical pumping of noble gases, dynamic nuclear polarization, and parahydrogen induced polarization, and SABRE. Today I will talk about parahydrogen induced polarization and SABRE. In case parahydrogen induced polarization, the hyperpolarized substrate was generated in hydrogenation reaction with parahydrogen. In here, the catalyst has important role because hydrogen addition must be pairwise. It means that both atoms from one hydrogen molecule must be added to one substrate molecule. In general, for generation of parahydrogen-induced polarization, the homogeneous hydrogenation catalysts are applied. It is due to the fact that most homogeneous catalysts activate dehydrogen by oxygen addition, which is pairwise. And in the slide show an image which was obtained by using homogeneous rhodium catalyst. It should be noted that application of homogeneous catalyst is not efficient because this catalyst very difficult quickly remove from reaction mixture, and this restrict application of homogeneous catalyst in medicine application because the solution of homogeneous catalyst is a very strong poison. In principle, we can fix a homogeneous catalyst on surface of surface, which makes possible to quickly separate the catalyst from reaction mixer. This catalyst name is immobilized catalyst. Today, this catalyst also applied for generation a hyperpolarized substrate, and the slide show two image which was recorded by using hyperpolarized gas, which was obtained by using immobilized catalyst. In case saber approach, the generation of hyperpolarized substrate occurs in reversible exchange reaction with parahydrogen. In the first stage, the substrate and parahydrogen must be combined within one complex compound, because only in this situation transfer hyperpolarization from hydrogen to any nuclei of substrate take place. After that, the hyperpolarized substrate removed from complex, and as a result, chemical non-modified hyperpolarized substrate which has non-equilibrium spin distribution is obtained. This approach also applied for generation of enhancement in mass signal. I would like in my work we applied both homogeneous and immobilized catalysts for generation of hyperpolarized substrate. And I would like to saber experiment, and I would like say any words about experiment method. In first stage, the reaction solution was bubbled with parahydrogen in magnetic field. After that, hydrogen flow is closed. The reaction solution quickly transferred in the mass spectrometer. In present work, we used a homogeneous iridium dihydride complex, which was synthesized from in situ from binuclear iridium complex. It is known that binuclear iridium this iridium, binuclear iridium complex can interact with with hydrogen, and hydrogenation of unsaturated ligand take place. So if reaction take place in solution of triphenylphosphine, that the hydrogen complex, which also coordinate 3 triphenylphosphine ligand, is formed. It is interesting that this complex in toluene solution is not stable, and there are several exchange processes of bonding hydrogen and bonding triphenylphosphine ligands with 3 hydrogen and triphenylphosphine. So, in other hand, we have initial condition for saber approach. We investigate this reaction and determinate reaction constant we can see on this slide. Moreover, if reaction solution is bubbled with parahydrogen in low magnetic field, and then quickly transferred reaction solution in NMR spectrometry, we can observe the high hyperpolarized signal from free and bond triphenylphosphine. It was found that this experiment was provided at 60 Celsius degree and 80 Celsius degree, and it was found that increase the temperature leads to increase of hyperpolarization. In particular, at 60 Celsius degree, the enhancement of phosphorus signal on free triphenylphosphine is about 100. In other hand, at 80 Celsius degrees, the enhancement of NMR signal was about 218. So, this significant amplification of NMR signal we used for recorded of NMR, recorded of image of reaction solution. It should be noted that when we applied thermal equilibrium, the signal in under thermal equilibrium, the NMR, the image is not recorded. Also, in our work, we applied immobilized iridium complex for generation of hyperpolarized substrate. This complex was prepared by interaction of phosphine-modified silica gel and binuclear iridium complex. It is known that in solution, this complex can interact with phosphorus atom, and in result, such complex can obtained. This complex was characterized by solid-state NMR, and it was found that phosphine-modified silica gel has only 2 signals. This signal refers to oxide phosphorus, which does not interact with iridium, but second, this signal refers to the phosphors of linker groups. After interaction with binuclear complex in NMR spectra, new signal is observed. This signal corresponds to immobilized species. This complex applied as catalyst in hydrogenation in liquid phase hydrogenation on phenylacetylene. It was found that after bubbling reaction solution of parahydrogen in NMR spectra of reaction mixture, hyperpolarized signal are observed. In this experiment, the enhancement factor is low, but the position of enhancement hyperpolarized signal can give important chemical information about wave of parahydrogen addition. For example, we can conclude that hydrogen addition in this case is not stereospecific because hyperpolarized observed on these protons, this and this. If hydrogenation, addition of hydrogen was stereospecifically, we can choose one.
Maybe you can summarize your.
Okay. So, okay. Also, the immobilized iridium complex applied for generation for hydrogenation in liquid phase. It was found that it was found that application of this catalyst can lead to the observation of hyperpolarized signal of reaction products. Also, the immobilized catalyst was applied in S-phase hydrogenation with parahydrogen, and it was found that its application can generate hyperpolarized product with significant enhancement of NMR signal. For example, if you can see when reaction take place in strong magnetic field, is a Pasadena approach, we can significant intensity hyperpolarized signal of reaction product. At the same time, when we recorded the equilibrium spectra, the signal from reaction products is very small. So, in conclusion.
I think very well. Maybe one, two short questions. Okay, please.
So it's good to see that you can hyperpolarize a great variety of compounds. I wonder, how to pick one to demonstrate in vivo, what would you choose? What, if you were going to use a hyperpolarized substance in vivo in animals, say, what would you choose to hyperpolarize?
I think that if introduce a hyperpolarized substrate in living object, then we can see all hyperpolarized signals. So not one.
No, I'm not explaining myself. You had to decide which experiment to do. What shall I hyperpolarize? What is the best demonstration in my method? What would you do?
Okay. In principle, theoretical enhancement in 7 Tesla magnetic field is about, if we have only pairwise addition, the enhancement was about
Probably very large. Oh, he forgot the number.
about 20,000.
Какое вещество самое лучшее?
It's okay? What's the substance is the best for in vivo applications?
For in vivo applications, the best substance which
Is your point? Okay.
the best substance for in vivo application can be
Non-toxic.
yes, of course, non-toxic.
Longest lifetime. Okay, require additional investigation.
I thought there was an interest in
It's the most interesting question, but still is open for future research. Okay. Maybe we can discuss afterwards this interesting point. Just let's thank you. Thank you very much. And we will move to the next talk. Next talk will be delivered by Alexei Kiryutin from the same institution. Subject polarization, ultra-wide magnetic field range is important question, which strength is necessary for polarization. So just we will informed about this.
Hello, everybody. Yes, I will try to. First of all, I would like to thank for the kind invitation to my recent results. I will talk about saber polarization and ultrawide magnetic field range. Ultrawide means really ultrawide, so we can switch in the 10 orders of magnitude. You already heard about saber a little bit, and thanks to Igor Kopchuk and Ivan Skopkin, that they explained about parahydrogen polarization. So the saber is one of the technique to polarize spins using parahydrogen. And saber is promising method to polarize liquids or solutes in solvents for NMR and MRI application. And the polarization level in this case, 20 or 30% is reachable. So I would like to tell you a little bit more detail about saber mechanism. In my opinion, saber active complex is a chemical engine to transfer polarization from parahydrogen to spin of interest. So the chemical stands for the parallel chemical exchange between the free substrate and the bound substrate to iridium, and the in parallel free parahydrogen solution to the bound hydrogen in iridium. And the engine, in my opinion, stands for the physical polarization redistribution in a short-lived active complex where spins substrate and spins hydride protons coupled by spin couplings. So, once again, so this is a schematic demonstration how the saber works. So, in the center you see the active catalyst. It's a hydride, which is stabilized by ligands, and in one case, in one side, you have a continuous chemical exchange between parahydrogen dissolved in solution, which is replaced always by the doubling, and on another side, you have also chemical exchange between the free substrate and the bound substrate. But this is not enough, actually. So this is only chemical way, and you need to fulfill the physical conditions. So the chemical conditions, so the exchange strongly depends on concentration, on the hydrogen pressure, temperature, and exchange rate. But it's not enough. The physical is, if we look close enough to the active complex, here, the two hydrogens are coupled by scalar spin-spin coupling to the nuclei, which is bound to iridium. And these two hydrogens are not magnetically equivalent, and in this network of coupling constant, the polarization transfer occurs, but you need to fulfill some conditions. Actually, magnetic field should be proper. So for proton polarization transfer, the matching conditions when the difference in chemical shift between, for example, this proton and these two protons should be matched with a J coupling. And in heterogeneous or heteronuclear case, the chemical shift difference between nitrogen and hydrogens should be matched with the sum of the spin-spin couplings. Since the chemical shift depends on magnetic field, then at some point you will have efficient polarization transfer. Now, how to study this field dependence? So you need to have some apparatus where you can easily change a magnetic field. So we decided to build in our institute apparatus, which is quite unique. We use, first of all, the straight field from the cryomagnet, which drops down from 9 Tesla to about 2 millitesla against the distance from this point to highest level. And we decide to move or shuttle the NMR sample by rack and pinion transmission using a stepper motor, which is controlled from an NMR console. And on top, if we want to go lower than the Earth's magnetic field, we introduce a magnetic shield, which is 3-layered cylinders made out of new material or thermal. And inside we installed the additional adjusting coils to change the magnetic field. So here is the scheme in details. So this is a cryomagnet. The sample is positioned on a plastic rack, which is transferred up and down by the stepper motor, which is controlled from NMR console, very precisely controlled. So every step is controlled by a pulse program. And when it enters the magnetic shield, the field drops down very rapidly. And this is a field profile from this position to this position. And in this case, we change current in the adjusting coils. So altogether, we can change magnetic field from about 10 nanotesla to 10 Tesla. This is a 9 order of magnitudes. And the field switching time between, let's say, lowest field and the highest field is less than 1/2 second. So it's quite rapid. We keep the high spectral resolution at the detection stage. It's a 0.5 hertz or 1 ppm. We can also, so we introduce the flexible Teflon tubing to the sample tube, and we can bubble parahydrogen or helium or argon or other gases up to 7 bars in the standard tube. The advantage is we can use the standard NMR probe, so we don't need to modify anything. Just bring new probes and you can use it. Currently, we have 2 probes, probe band and TXI. We can detect almost any nuclei. This looks quite simple, and since it has only one moving part, it's very robust. So together it moves already more than 100 shuttles, and it's still stable. And it's very fast and simple to assemble. Just 10 minutes and we can remove everything, and the spectrometer is ready for other users. So now this is results. The pyridine is a classical example for the Saber polarization, because pyridine bonds very well to the iridium, and well, in pyridine all conditions is met. That's why if you measure now a bubble solution containing pyridine and complex at different fields and detect it always at one field, so we can measure the field dependence of the Saber polarization, and you see only actually at 2 fields you have very efficient polarization transfer. And as I said, in this case, we have matched conditions between J coupling, H-J coupling, and chemical shift difference between protons. And in this case, it's very low field, so it's less than 1 microtesla, usually 0.5 microtesla or 0.1 microtesla. In this case, we match the conditions when the J coupling is equal to the chemical shift difference between nitrogen and proton. Now, this is example I like. So if you can buy the metronidazole, which is available in the pharmacy. You can solve it in methanol and try to detect normal NMR N15 spectrum. You will get nothing because the natural abundance of N15 is very low. The nuclei is not very sensitive, so even half an hour you will get nothing. But if you bubble at the proper conditions and within single scan, you will get very nice result NMR spectrum of N15 natural abundance nuclei. And in this case, we spend only 10 seconds for creating polarization and one scan. So now, if we vary magnetic field, so in my work I vary magnetic field in ultra low field, we found some dependence. We try to model it, and in a 3-spin system, very simple case, we still can, we understand the position of this maximum is coincide quite well. The 10 curves between protons is very good, so it looks like a 2. But we also have seen that not only one nitrogen is polarized, but all others is also visible. Well, enhancement is very small, only 100 or 400, but it's still possible to see. And this is proton saber polarization in a different scale of magnetic fields, but also if we try to simulate and vary coupling between two hydrides, well, -10 coincides very well, and the 10 or 8 is very good. Now, what we can do with such a polarization? We decide to measure relaxation of N15. There was a question how long it is. So in this case, using such a device, we can prepare very strong polarization in ultra low field. Then we can shuttle our sample to another field, let it relax, and then measure at detection point. Then you can change relaxation delay and measure how the polarization decays. You can measure T1, and then you can change field, and you can measure T1 over the field. That's an example how the polarization or enhancement decays in time, in the minutes, and how the spectrum looks like. So even after 1,000 seconds, you can still detect the N15 polarization from natural abundance metronidazole, which is used as an antibiologic and anti-proposal medication. This is final results. We have applied this protocol experimental, and we have measured the relaxation time of this nuclei and at position 3, and you see how it depends on the magnetic field. So in most of the range is relaxed very fast, especially in the conditions where we produce it relaxes within, I think, 10 seconds or even 2 seconds in this case. But if you go to this intermediate field from 0.1 to 1 Tesla, this is exactly where the MRI scanners works, or more or less. You can reach the relaxation up to 400 seconds, several minutes. Yeah, so and in this case, I would say that this is a storage field, and in this case, it's a polarization field. Again, what is the advantages? You can create polarization very fast, within 20 seconds, and then move to proper field. Actually, you can store it in the permanent magnets. This is exactly the strength of the permanent magnets, and you can transfer. So I think this example you can apply for MRI. As a conclusion, we found the optimal conditions, optimal magnetic field for proton and nitrogen saber polarization, for metronidazole and pyridine. So for proton, it is between 5 and 20 millitesla. For N15, it's in the range of sub-micro Tesla, 100 to 1,000 Tesla. And we have measured nitrogen relaxation time or the wide magnetic field range between 200 nanometers and 9. Well, the take-home message from my talk that it is very simple to create polarization at ultra-low field and store it in a field of 1 to 1 Tesla. Saber method is quite simple and cheap because you can invest $500,000 to have the homemade parahydrogen generator. You can produce it in a liquid nitrogen conditions, which is quite cheap. And then you need to just supply liquid nitrogen and of course the reduced. Yeah, I would like to thank my supervisors, Alexander Yukovsky, in development and partner team, and thank you for your attention.
Very interesting talk. Probably we have time for 1 short questions. Okay.
Yeah, on your relaxation measurements, your field cycle, getting it up. One result, I think, is the question about this. You have a very long time, sort of up to Tesla. Once you go beyond that, you get into a region of very rapid increase of the field, very strong field gradients. And just the diffusional motion in the field gradient can cause relaxation.
And was,
We have considered that it's typically considered problem for gases, for heating, in particular form at much lower grades. But I wonder that whether you have some problem.
well, diffusion or convection in liquids detectable on times of minutes. That's true. But of course, then if you would have some peaks or drastic changes in the field, and then you have a gradient which covers this field, of course, then you will smooth out this picture. But well, since it's like a smooth curve,
No, it's all fine. The question is whether that's all CSA that kicks in, or whether you have an additional.
well,
Which would be good
I
news
think
for
it's
you.
a CSA because I think I try to simulate or fit the last 5 points and they perfectly align with the parabola. So, yeah.
Another questions?
It's an half question, but many years ago, I was interested in contamination reactions. I was trying to do that with 10-15 NMR. I gave up. Perfect.
Yeah, actually,
I remember in biochemistry quite a lot of these reactions, and it's very hard to follow them. It's usually good with someone.
Okay, let's send speaker again. Next talk is delivered by Oleg Salnikov from Chemical Institution. Polarized contact agents produced by heterogeneous oxidation with Parahydrogen.
Okay, so good afternoon, dear colleagues. I represent the group of Professor Igor Kopchuk at the International Tomography Center, and I will tell you about hyperpolarized contrast agents produced by heterogeneous hydrogenation with parahydrogen. First, I remind you some parahydrogen-induced polarization basics. So you already know that there are 2 nuclear spin isomers of hydrogen molecules, orthohydrogen and parahydrogen, and that you can reach hydrogen with far isomer by cooling it down to low temperatures in the presence of paramagnetic compounds such as ferric hydroxide or charcoal. And parahydrogen itself has 0 nuclear spin, and therefore it is invisible in NMR. However, if one breaks the symmetry of H atoms in a parahydrogen molecule, one can obtain hyperpolarization, and to this you need pairwise addition of parahydrogen to some asymmetric and saturated substrate. Pairwise hydrogen addition means that 2 atoms from the same parahydrogen molecule end up in the same molecular reaction product. So in this case, your NMR signal is significantly enhanced,
and also the signals take characteristic antiphase shape. It has been already told today that there are two modalities of FIP, homogeneous FIP and heterogeneous FIP. And homogeneous FIP is based on the use of homogeneous catalysts, which are transition metal complexes, which provide 100% pairwise hydrogen addition and therefore high NMR signal enhancement. However, these catalysts are toxic and thus they should be separated from your hyperpolarized product. And this separation is not an easy task. In contrast, heterogeneous catalysts, which are usually metal nanoparticles supported on some porous support, over this catalyst, hydrogen adsorption is dissociated, and this leads to quite low NMR signal enhancement. However, this catalyst can be easily separated from the reaction product, and also they enable continuous production of hyperpolarized liquids and gases, and they possess high catalytic activity and stability. From the morning session, you already know that C15 hyperpolarized carboxylates, especially pyruvate, but also acetate, lactate, and others, they are important metabolic contrast agents for C15 MRI. For example, hyperpolarized pyruvate can be used for tumor diagnosis and to monitor response to tumor treatment. And the methodology is already applied in humans, for example, for prostate cancer. However, hyperpolarization of these compounds is achieved by dissolution dynamic nuclear polarization, which is a good technique, but it has a significant drawback because it requires very expensive and sophisticated equipment, so it is not affordable by most of the clinical hospitals, by most of the hospitals around the globe. So, Parahydrogen-induced polarization represents a cheaper alternative to DNP. However, the problem is that it is not possible to obtain pyruvate or acetate or lactate by parahydrogen-induced polarization directly. This is due to the fact that there is no corresponding unsaturated precursor which can be hydrogenated to form these compounds. However, 3 years ago, Rene and coworkers introduced FIP side hydrogenation approach, or FIP-SAH, which allows to produce hyperpolarized carboxylate. This approach is based on the use of ester, which contains unsaturated alcoholic moiety and carboxylic moiety of interest, for example, propyl pyruvate. So this compound was homogeneously hydrogenated by parahydrogen, and in the resultant hydrogenated ester, polarization was transferred from protons to C15 nuclei using magnetic field cycling. Then the ester was hydrolyzed with sodium hydroxide solution. The excess of sodium hydroxide was neutralized with deuterium chloride, and in the end, aqueous phase was separated. So, using this approach, one can obtain C15 hyperpolarized carboxylates, for example, C15 hyperpolarized pyruvate in aqueous solution. An alternative approach is the use of heterogeneous catalysts for FIP-SAH. We started to explore this possibility 2 years ago, and we started from C15 labeled vinyl acetate. We hydrogenated it with parahydrogen over the rhodium catalyst supported on titania in organic solvents, benzene and methanol, and it was found that this approach is successful and it is possible to detect C15 hyperpolarization on ethyl acetate. Also, it is important that in case of methanol, it was also possible to detect C15 hyperpolarization with the use of natural abundance substrate. And also, this approach also worked well in water, in aqueous phase hydrogenation. However, signal enhancement was slightly lower in this case. Recently, we performed systematic HET-FIP-SAH study of several acetates and pyruvates. So in total, we used 6 compounds, 3 acetate esters and 3 pyruvate esters, these 3 different unsaturated alcoholic moieties, which are allyl, propargyl, and vinyl. First of all, these compounds are synthesized in both C15 labeled and unlabeled forms. The synthesis of allyl and propargyl esters was carried out by esterification of carboxylic acid of interest with corresponding alcohol. The synthesis of C15 labeled vinyl acetate was carried out by transformation of labeled acetic acid with vinyl laurate in the presence of ruthenium chloride. However, this reaction was not successful for the synthesis of vinyl pyruvate, so no reaction product was observed. We succeeded when we used vinyl acetate for transvinylation and used palladium acetate as a catalyst. However, so we obtained vinyl pyruvate, but the yield of the reaction was only 6%, so we didn't synthesize the C15 labeled compound using this reaction. Next, the synthesized compounds were used for HET-FIP studies. In case of acetates, it was possible to detect proton polarization and carbon polarization in both methanol and aqueous solutions for all of the substrates originated. It should be mentioned that vinyl acetate and allyl acetate gave quite similar NMR signal enhancement. However, propargyl acetate was significantly less efficient as a substrate. Most likely, this is due to the low catalytic activity of rhodium catalyst in hydrogenation of triple bonds compared to hydrogenation of double bonds. In case of pyruvates, it was possible to obtain proton polarization for all of the precursors hydrogenated. However, it was not possible to detect C15 hyperpolarization. Generally, it should be mentioned that proton polarization in case of pyruvates was lower than in case of acetates. And in case of propargyl pyruvate, it is also due to low catalytic activity. And in case of vinyl and allyl pyruvate, the general catalytic activity of the catalyst was quite high, but the selectivity was low. So, for example, in allyl pyruvate hydrogenation, the conversion was 52%, but selectivity to propyl pyruvate was only 21%. Next, let's move to the second part of my talk, which is devoted to hyperpolarized gases. You already heard yesterday a lot about hyperpolarized noble gases such as xenon, helium. So these hyperpolarized gases can be used for MRI visualization of lungs, for the diagnostics of lung diseases such as COPD. However, hyperpolarization of these compounds, of these gases, is carried out using spin exchange optical pumping, which, as well as DNP, requires quite expensive and sophisticated equipment. Another problem is that for detection of these gases, you need special multinuclear capabilities detection in your MRI scanner, and it is not possible on standard clinical MRI scanners. So here, parahydrogen-induced polarization is also a promising alternative because it allows to obtain proton hyperpolarized gases. An example is proton hyperpolarized propane gas. It can be obtained from propylene by heterogeneous hydrogenation with parahydrogen. Some years ago, we showed that it is possible to obtain propane with 1% proton polarization using rhodium supported on titanium catalyst, and the resultant hyperpolarized propane gas can be used for 3D MRI of model phantoms with high resolution. However, these images were obtained in continuous flow mode with 15 milliliter per second gas flow rate, and also the size of the phantoms was not high. So the phantoms actually just represented a tubing with the diameter about several millimeters. So recently we made a clinical scale propane polarizer. So this polarizer operates in batch mode. The idea of polarizer is to prepare a mixture of propylene and parahydrogen in a mixing chamber. The pressure in this mixture is high, it's 17 atmospheres actually, and then this mixture is quickly released to atmosphere, First, it goes through the catalytic reactor, which had 3 sections. In the first section, gas is heated with an oven, and in the second section, hydrogenation takes place and hyperpolarized propane is formed. And in the third section, the gas is cooled down using a fan. After the reactor, the resultant hyperpolarized propane goes to an imaging phantom, which is located inside the preclinical MRI scanner. And the gas flow for the phantom can be rapidly interrupted using bypass line. And the pressure inside the phantom is kept about 7 atmospheres using a safety valve. So this polarizer allows to quickly produce half a liter of hyperpolarized propane gas with 1% proton polarization just in 2 seconds. And important is that despite the high gas flow rates during the gas release, in this polarizer we can achieve 100% conversion of propylene. This is due to the use of high catalyst load inside the reactor. So using this polarizer, we obtained high resolution 2D MR images. Also, it is important that all of these images, except the top left one, which is image of flowing propane gas, the other 3 images are images of stopped propane gas. So it is possible to stop the gas flow and get good quality image, good resolution image with stopped gas. And also it is possible to get an image after several seconds after interruption of gas flow. Another possible approach for production of hyperpolarized propane is hydrogenation of cyclopropane. Cyclopropane is an interesting substrate because it is non-toxic and it has a long history of previous use as an anesthetic gas. In principle, heterogeneous hydrogenation of cyclopropane can lead to 3 types of hyperpolarized propane molecules. So the first type is hyperpolarized propane molecules with parahydrogen-derived protons in magnetically non-equivalent positions, similar to those molecules produced in hydrogenation of propylene. However, there are also other routes of hydrogenation are possible, which leads to formation of hyperpolarized propane molecules with parahydrogen-derived protons in magnetically equivalent positions, like this or this. And these types of molecules should be NMR invisible due to magnetic equivalence of protons. At the same time, they may possess significantly longer lifetime compared to molecules of this type. However, despite this possible quite complex chemistry, we found that hydrogenation of cyclopropane can, of course, it can give us hyperpolarized propane gas, but important is that propane polarization is remarkably high. It's significantly higher than in the case of hydrogenation of propylene. So the highest observed polarization was 2.4% for propane. However, the problem is quite low conversion, which was 3% the highest. However, we think that it is possible to increase conversion by the use of even higher catalyst loads. So despite this low conversion, it was possible to use the resultant hyperpolarized propane gas for MRI. So we also obtained the MRI of stopped flow gas in a 5.5 milliliter phantom. And an interesting result, which may explain why we obtained such high polarization in cyclopropane hydrogenation, is the effect of cyclopropane treatment on the catalyst's performance in hydrogenation of propylene with parahydrogen. It was found that the cyclopropane treatment leads to about 5-fold increase in proton polarization for propane obtained in propylene hydrogenation. However, at the same time, propylene conversion is decreased from 100% to 70%. So this indicates that cyclopropane acts as a poison to the catalyst. So it possibly blocks the catalyst surface, which leads to increase of the probability of pairwise hydrogen addition. However, at the same time, the conversion of the reactant drops down. So I tried to convince you that heterogeneous FIP is a promising approach for production of hyperpolarized molecules both in solution and in the gas phase, and that possibly will have some future applications in clinic. And in the end, I would like to thank my colleagues from International Tomography Center and also our collaborators from the United States, especially Professor Edward Chekmenov, and also our colleagues from Boryskov Institute of Catalysis, and thank you for your kind attention.
We have time for several questions.
About the gas phase, of course, I'm interested in that. I think you mentioned already the relaxation times or something. Second, but can we go on to longer times? How is it with propane or cyclopropane? Relaxation time, how is the function of pressure?
So actually, the hydropolarized propylene gas, which we observe in cyclopropane hydrogenation, it's really is the same hyperpolarized propane which we observe in propylene hydrogenation. So the substrate does not have any effect on the product we obtain. The fact is that in case of cyclopropane hydrogenation, we may also have other types of molecules which we just cannot observe using an thermometer. So we don't know anything about these molecules. I mean, this type molecules or this type molecules. So we don't know anything about them. And this type of molecules, they are the same as in the case of propylene hydrogenation. So the relaxation time is also should be the same.
Okay, and the relaxation time are what? I mean,
It actually depends on conditions. So it's atmospheric pressure. Relaxation time for propane is about 0.6 seconds. So if you increase the pressure, relaxation time is high. For example, at 7 atmospheres, it is about, I think about 5 or 7 seconds, something like this. And it also depends on the magnetic field. So in the low magnetic field, for example, 50 millitesla in this magnetic field at higher pressures, we can obtain up to about 12 seconds relaxation time.
So the major mechanism here is spin rotation? Or
Yes, in the gas phase, spin rotation.
one last, when you have the conversion factor, so you have a hydropolarization of, let's say, 3%, and you have a conversion factor. Am I right that you have to then basically multiply the two to get some real factor? I try to just guesstimate what the signal would be for a pulmonary application. Is the conversion rate then multiply the polarization to get some realistic polarization of what you can expect in terms of signal?
For FIP experiments, both conversion and your polarization, they are both very important. So you need to have both high conversion and both high polarization level to get a
So if I have
good
3%
signal.
polarization by 10% conversion,
That's
something similar signal as I would have the same signal as I would have at 2.3% polarization with 100%.
Yes,
Okay.
in case if your relaxation is the same. So
Yeah,
the
well,
polarization depends on the relaxation, surely.
Other
question.
Okay.
You used propane instead of normal bases. And it's
Well, actually, it's a good question, but propane itself is not toxic. So there were some toxicity studies some years ago, and it is not toxic in a wide range of concentrations, actually. So the problem can be with possible explosions. Of course, this problem should be solved for clinical administration. However, I think it is possible to make a technology based on this actually.
Especially for lab investigation.
Yes, of course, but
Okay.
well, actually, currently there are no examples of the use of hyperpolarized propane in vivo, at least no published examples. There was some poster on the conference in the US, I think a year ago. So they used thermally polarized propane for an imaging of the mouse, I think, or some laboratory animals.
It's already started a view. Okay, thank you, Alex. We just arrived to the last talk of our session. Introduced by Andrei Savelov, devoted to functional polarization. This talk recovery of post-control function and understanding of functional MRI via feedback.
Thank you. Good evening. Okay. So let me relax our highly polarized session. I will talk about what functional MRI and EEG together can do to help stroke patients. Just a few words about how it works at all at the functional MRI. For those who didn't met this type of MRI, which primarily oriented on anatomic changes in anatomic structures. But functional MRI deals with function of the brain and the effect observed, so-called blood oxygenation level dependence, is based on oxygen delivery to neurons. In the resting brain, on the left side, you see the neuron in its basic state when some oxygen is delivered, consumed, and deoxyhemoglobin flows down the venous stream. So some stable equilibrium concentration of deoxyform exists in this tissue, and when an activity comes and a neuronal group neurons are fired, then immediate vascular reaction follows, which delivers an excess amount of oxygenated blood to the active area. And what happens is that the deoxyhemoglobin is actually washed out of tissue, and its concentration drops. This physiological effect leads to increase in the mass signal because the deoxyhemoglobin is paramagnetic and acts as effective T2 star relaxation agent. When this concentration drops, so we have increase in the signal. This increase indicates that the area is active. So in the objectives of our work is to combine fMRI and EEG and produce feedback closed loop system so that the subject of the experiment can see and feel what happens in his or her brain. So what you need to perform this experiment, first of all, you need, of course, an MRI scanner. Second, you need an EEG system compatible to MRI. Why together? Because MRI and EEG well fit together. MRI has a relatively high resolution, tens of microliters per voxel, and observes events of hemoglobin moving oxygen delivery in time frame of seconds, of 5 to 10 seconds. At the same time, the EEG are very well at temporal resolution, so we see in milliseconds range everything, and it's known that the location of EEG signal sources will pose problems, so it's not so well at spatial resolution. Together, we see when and where you have your actions performed. You have both time and spatial position. Also, you need some looking simple but sophisticated devices made to be used right in the scanner. So it's stimulus delivery monitors, earphones, and response systems. Some more. Here is the workplace of the operator of the whole system. You may see that on the left side there is a monitor for this scanner, which process the MR signal and delivers the bolt effect and localizes it very well. On the right side is a EEG registration point, and in the center the stimulus display, which is also available. I'm sorry, should play. Should I play it? No. Okay, movie doesn't work. Don't know why. It wasn't well before. You can see that this display is duplicated in the magnet, near the magnet, so the subject can see it. What you see also on the front display, it's a yellow disk, which size depends on the activity of the target zone. Experiment itself set in 4 steps. First, we make 8 circles, show a hand to the subject, and he should move his fingers. When hand removes, it stops. So we have identified this way area responsible for post-stroke activity of a limb. After that, we perform mental task. So motor images task when the subject performs the same actions but not really moving the fingers. He images this movement. So also 10 blocks, 10 repetitions, and after that, having localized the responsible area, we show this yellow disk to him so that he can closed loop feedback. He sees how his damaged fingers, his damaged brain, which regulates fingers, acts in this moment. So, and after that, the final block repeats the second. So again, without feedback, the subject should try to evoke this activation by mental strange, by additional activation of its own brain. Oh, now you can see how it works. So when the hand is on the screen, we show this yellow disk to our patient, and he tries to learn how to regulate own brain activity. So we have 12 subjects in this project up to now. It's a kind of work in progress. The 4 to 14 sessions of such training was performed up to now, and I'll show the results of one of our best trainees. The upper left is his first scan. The red and yellow spots indicate the areas which were active at the very first attempt to move the fingers. You see that the activation is diffuse, and almost all the brain tries to do this complex task because his motor skills are damaged by stroke. Next, you see the picture 2 months later, and 4 months later, and 6 months later, and you will see that some improvement, I would say, good improvement takes place. Oops, sorry. Yes, and the picture comes very close to what we could expect at healthy patient. So one well-defined region takes responsibility for this movement. Its opposite side is he has right side stroke, so his left hand is affected. Right hand affected in less, but also we have some dynamic which comes to well localized activation in the left hemisphere. Looking not only on localization of activation, but also networks of activation, we see the following picture. The network is the ensemble of neurons which acts in the same pace. So if we before we have seen the localized activation which corresponds to some periodic task, the networks are not task dependent. At least they not use explicit information about how the task is designed. We simply search for groups of neurons which act in the same manner. So the number of such networks are identified. Most of well-known default mode network which is active at rest. Also some other depicted here. And what we have seen in our patients is that the dynamic of the networks changes in opposite way at left wrist, which is affected, and the right wrist, which is not affected, and the changes in the dynamic at opposite sides. So the blue color means that we have reduced connectivity of and reduced activity of networks, which generally corresponds to what we have seen the transition between this diffuse activation of the whole brain to correct or localized to some specialized area. The right wrist demonstrates the opposite. We have increase in the network construction and in building up the networks. We can suppose that it's right left hemisphere takes some control over damaged left one. And last not least, we have pictured the most statistically significant components of the networks and plotted it over course of years of training. What we see here is axis of real work and mental work. What we try to achieve is alignment along the diagonal. It would mean that we have trained the person to mentally reproduce the real movement. So what would indicate that it has mastered the activation of his brain completely. So for his no great difference between real and imaginary work. In fact, we see something not yet explained. At the first half to 1 year, indeed the correlation, each dot is some correlated network. It moves to diagonal, which is expected, but after that, this movement continues. They do not line up along this diagonal. It may indicate that we overtrain our patient. So that means that the training we can stop at some moment, which is not yet understood fully, but both functional MRI on the left side and EEG demonstrate that we have achieved some good result, but maybe in some cases we even continue when we should be already done. So, as a conclusion, I would say that the dynamic of restoration of the activity of the centimeter cortex suggests that the new neural networks are built, and the interaction between hemispheres support the theory that damaged hemisphere is replaced by not damaged one in motor functions. And this technology may be used as a therapeutic, I would say, technology to help not only by stroke, but also for a large or wide range of neurological and psychological diseases, to help patients to recover their state and rise their life level. Let's say so. Thank you.
Thank you for a nice talk. Questions?
Obviously, it's a good idea to use fMRI if we want to understand the functional neurological basis for the recovery. But I was thinking in practical terms to aid the patient. You need the fMRI, and your EEG seems to be doing quite a good job, and maybe also to consider near infrared. So there's a scientific question of I want to understand what's going on, but a practical one of I want to deliver recovery to this person. Can I get away with EEG? Or do I need to?
Yes, it's a very well and exact question. You may also ask how much costs are involved if you many times bring your patient to the scanner. The idea is to identify the EEG patterns which correspond to correct activations on the fMRI scale. We do it indeed. We are trying to establish some connection between EEG events, which are quick and which predict some fMRI events. And obviously, we, of course, tend to train our patients with EEG only, with control of fMRI, of course, but EEG sessions will be much more frequent than fMRI.
Other questions?
Thank you.
Organizers can announce some for the evening and tomorrow day of our conference.
Dear colleagues, now we shall continue our cooperation at the British Embassy. So together we need to take minibuses because the traffic jam there in the center is very packed. So we need the small buses to get there. And our buses will wait us just the same place we were taking the bus yesterday. So it's just nearby this building in 10 minutes. So we shall just gather downstairs at the entrance of the building and then move all together to the buses, okay? In 10 minutes, we shall wait you there. So tomorrow morning, we shall start just as scheduled. We have a very packed program for tomorrow morning, and then we shall have an excursion. And the second half of the day will be at the physics department. So don't mix up the place, okay? In the afternoon, it will be different buildings. We shall notify you tomorrow afternoon, okay? So any questions, please ask. We probably, I think, all of you are already in the list to admittance to the British Embassy. So if you don't, if you are not sure if you are in the list, please come to our organizers to check if your family name is there. Okay. So we almost all participants are in the list, almost. But if you didn't register on the conference website or something else, there may be